So I've recently started learning assembly, a low-level programming language, basically a human-readable form of ones and zeros. It's super important for malware analysts, because with a program called disassembler, you can turn any executable, any binary, into an assembly code, and if you know how to read an assembly code, then anything is open source to you. But it's not all that beautiful. Assembly can be and is extremely confusing. But don't worry, in today's video I'm gonna give you some foundations and explain some basics so that you can smoothly start your assembly journey. And one more thing before we start, if you wanna see more hacking and cybersecurity related stuff, check out my Twitter, link in the description. And without further ado, let's jump into the registers. Registers are fast and small storage locations directly within the CPU, used to store data that is immediately needed during processing. Of course, amount and types of registers vary among CPUs, but in today's video we're gonna focus solely on Intel's x86 architecture. The first register I wanna show you is called EAX. It is used to store a return value of a function, that's its primary purpose, and it is 32-bit long, as all the registers in x86 architecture are, of course. And as you can see, there is a way to access specific parts of each register. The naming convention is the same among all of them, but I'm just showing it on EAX example. If you remove the E at the beginning and refer in your code just to AX, you will be referring to the lower 16 bits of EAX. And if you go even deeper and refer to AL in your code, you will be referring to the lowest 8-bit. And of course, AH is the higher 8-bit of AX. So it's just a way to access certain parts of registers, and it may come very handy. Okay, but how do you actually write a value to a register? Well, you do it with MOV instruction. As you can see, the syntax is fairly simple. First comes the instruction name, always. This is a convention in assembly. First thing is the instruction name. Then there is a destination, which is EAX, in our case, of course. And then there is a source, which can be a value. It can be another register, because you can move values from registers to registers. It can be anything else, but right now this is like a value 5. And this is the same as, for example, EAX equals 5. So this is of course a very simple example. You will see a lot more in this video. But for now, I just want you to understand how these syntax work and just, sort of know that this is basically EAX equals 5. Different registers can have different purposes. As I mentioned before, EAX is used to store a return value of a function. ECX is often used as a loop counter. ESP is a stack pointer register. It basically points to the top of the stack, and if you don't know what the stack is, don't worry, it will be covered later in this video. But the idea is that you have to learn these purposes, and on the screen right now you see a list. It's not very big, so pause and read through it. It's a part of an assembly cheat sheet. It is linked down in the description of this video, so you're welcome to download it. It's not mine, I found it on the internet, but it is like open source and for everyone to use, so I'm sharing it. So let me show you how it works in practice. We have a completely new project in Visual Studio. Let's right click here on the project and go to Build Dependencies, Build Customization, and select MASM here. Click OK. And let me create a new file. Let's call it main.asm. And again, right click on the file, Properties, and choose item type Microsoft Macro Assembler here. Apply and OK. We start by specifying the architecture like this. .model flat and .code to open a code section. Inside this code section we will write our assembly code. We start by creating a procedure. We call the procedure main. Procedures are like functions in high-level programming language, like in C. You see you have a main function, here you have a main procedure. So let's do first thing. Let's move to EAX a value of 5, for example. Move. Okay, and now let's use the add instruction to add EAX 8. And now, as the last thing, let's move the EAX value to EBX register, like this. So we can do some basic arithmetics, and so you can see how this MOV instruction really works. And we end the procedure by specifying the procedure name and P. And as we finish the function, also don't forget the ret instruction at the end of each procedure. And here you type end main, like this. And it should work. Let me fire up a debugger here, a breakpoint here. Make sure you have x86 specified on the top, and let's compile it. Alright, last thing, we want to see the register values like this. So let me step over. As you can see, EAX is now 5. We moved a value 5 to EAX. Now let's add 8. Here you can see D, which is 13 in hexadecimal. Okay, next we want to move this value, so the D value, to EBX. So watch how EBX changes. We have D, so we have the same registers, and then we return, and nothing, we don't really catch the return anything anywhere, so it will throw an error here. But basically you can see how this add and move instruction work. Let me also maybe modify it here. Let's go with subtract EBX 7, for example. Whatever, just to show another arithmetics instruction. So let's debug window registers. Okay, so again, move 5 here, add 8, move 8, move D here, and subtract 7, and we have 6. So that's how the move instruction work. And let's move on to the next topic. Let's try some multiplication. This instruction is a little different. Let me delete this. So we have EAX, and if we, let's say, move EBX 8, okay, and then type mul EBX, then it means that EBX will be multiplied by EAX. Basically, the parameter that you specified here will be multiplied by whatever value is in EAX register, and the product will be saved in EDX and EAX in both registers at once. And why is that? Because the value, the product of multiplication, can be significantly bigger than the operands, so you basically need to save some space. And I will show you how it works. So of course, let's fire up a debugger with the correct window, like this. So we move 5 to EAX, we move 8 to EBX, and you can see that after executing mul, we have in EAX the 28 in hexadecimal, of course, and EDX changed to all zeros. That's because the EDX was reserved for the extent. If there is a need to extend the EAX, it can always be done here. Notice that after whatever we multiply, let's like change the values a little bit. Whatever we multiply, EDX is always changing after the multiplication instruction. Let's test it again. As you can see, whatever changes, it's highlighted in red color. Alright, so EDX also changed, but there are all zeros, so we need to like make those a little bigger, like this maybe, so that we exceed the size of 32-bit of one register. Let's try this. Okay, still too little values. Maybe like this. Okay, wait, I forgot the register window. Okay, and now you can see that there was not enough space in EAX only, so EDX helped with by adding additional space. And the same principle is used in division. Let me show you. We do it like this. First you want to modify the value in EBX. Let's put 10,000 here. And now, using the div instruction with EBX parameter, we basically say that divide whatever is in EDX and EAX combined by the value in EBX. We know that in EDX and EAX is now the value of 10,000 times whatever is here, 8 million. So now we will hopefully have in EDX and EAX, we will have the value of 8 million, right? Because this divided by this will give us this. So let me fire up a debugger and registers. Okay, multiplication goes here. We are moving 10,000 here, and the division here. As you can see, those registers were modified indeed. Let's copy the value of EAX. And I have a converter somewhere here. Hexadecimal value is this, and we should get 8 million. 8 and 6 zeros. So everything is working fine. So that's how you do a division. Okay, so for this section in the video, I want to show two more instructions, shift left and shift right. They are used to operate on bits. So shift left, it just shifts all the bits to the left by a specified value. So if you have 001 and shift left 1, you will have 010. But let me demonstrate it. Let's move 0 to EX like this. Now, or maybe no, let's move 0, 1, 2, 3, 4, 5, 6, 7 like this in binary. And now if you shift left, by 1 like this, it's not gonna be very visible in this debugger because it's an extremely small value. It's 1 byte in 4 byte register. So wait, debug Windows registry. Okay. As you can see, this got changed to 7F. Okay. And this is, let me go to the converter. It's gonna be better visualized. So we go from binary to decimal first. It is 127, as you can see. And this register holds exactly the same value, but in hexadecimal, 127. Now, if you shift left by 1, let's execute this operation. We should have completely different value, which is 254. And if you think about it, if you go to binary again and we typed 0, 1, 2, 3, 4, 5, 6, 7, right? It was 126. If you move 1 bit left and 0 to on the right, because the shift instruction goes to the side and appends 0 on the other side. I hope you understand it. So if you go to the left, we move all the value to the left and add 0 on the right. So it's 1, 2, 3, 4, 5, 6, 7, 8. And if you convert, it's 254. And let's do the same, but with shift right. So if you go SHR for shift right, let me compile it one more time. And let's open up registers window. All right, we have the same value, 127. And if we shift right, we have a different value. Let's copy it. To hexadecimal, we have 63. And if you look at the decimal one more time, we started with 0, 1, 2, 3, 4, 5, 6, 7. what we do is shift right by 1. So we add a 0 to the beginning, basically. And with convert, we get 63. Now when you have an idea of how basic instructions work, let me introduce you to the stack. The stack is a data structure that follows last in first out principle. Think about it like a stack of plates. You can only put a plate on top of this stack, and you can only remove a plate from the top. And your CPU does exactly that, with push and pop instructions. You use push instruction to push a value onto the top of the stack, and you use pop instruction to remove a value from the top of the stack. Let me show you an example. Let's look at this representation of memory. We have rows, each one is 4 bytes, each has its own address, and we have the ESP register that is pointing to the top of the stack. Now, if we want to push a value 4, we execute this instruction, and we have a value 4 in our stack. Now, as you can see, ESP moved. ESP is again pointing to the top of the stack. Value 4 is in it, and with each next push instruction, ESP will be moving again to the top, to the top, to the top. Why this is so important? Well, if we want to pop a value from the stack, if we want to remove it from the stack, we need to know which one is at the top, and ESP tells us exactly this. So we use pop instruction and the value that we specify with pop. So we say pop and something. This is the destination to where we will save the value from register, from the stack, sorry. And we want to save it in EBX. So let's execute it. As you can see, EBX is now equal to 20. And ESP, the stack pointer was again moved to the top of the stack. Now, what you can see is that the value 20 remains. It remains on the stack. It is not deleted, but it doesn't remain on the stack. It remains in memory. But the stack is actually not there anymore. The top of the stack is where ESP points to. So 20, the value 20 is out of the stack. It is now in the EBX register. And if we want to pop ECX, so we want to pop another value from the top of the stack to ECX, we will see this. We see that, sorry, there's a mistake here. There should be ECX, not EBX. But as you can see, ESP points to the top of the stack again. And these values are in memory because no one deleted them, but they are not on the stack anymore. So it's very important that you understand this convention of pushing and popping and how this works, because all functions base on the stack. If you have function arguments, they are on the stack. Local variables are on the stack. So this is important that you understand the concept of a stack. And of course, it will be much easier to see it in action. So let me show you. Okay, so we have a clean procedure here. And let's start writing some code. So whenever you work with a stack, you need to write something called stack prolog. It looks like this. You push EBP and move EBP ESP. What does it do? First instruction pushes the value from EBP to the stack. Second instruction moves the value from ESP to EBP, or maybe copies the value from ESP to EBP, so that they point to the same location right now. ESP is a stack pointer, as I said. Sorry. EBP is a stack base pointer. It always points to the base of the stack. It will allow, in the more advanced functions, which we won't be dealing in this video, it will allow for accessing some variables, some parameters. So this is important. And at the end of each function, you should always write an epilogue, which is pop, EBP, and return, like this. And whatever you do with this stack, you do in the middle here. Okay, so let me actually demonstrate the push and pop instructions. Let's move EAX 5, let's say. Let me push the EAX value to the stack. And maybe now we can pop the value from the stack to EBX. And this will basically move the value 5 to the EBX. Let's run the debugger. Registers. Alright, so first we do the prologue. We move the value 5 here. We push it to the stack. As you can see, the stack pointer changed. It is red, it changed with this push value. And we pop EBX. What will it do? Well, it will change the stack pointer. And EBX is now 5. So everything works. Now we pop EBP and return, and we finish our program. So that's how the stack structure works. That's how those push and pop instruction works. It's a fairly simple concept, but it can take some time to understand and get a hand of. Now, some of you may ask, do we have variables in assembly? And yes, we do have. They are called labels. You will see that later in this video, labels are referred to both variables and markers in the code, because they are used basically to mark a certain location, a certain address. So if I use value, which is the label name, dword, which is a type, and then 5, value label will hold an address of value 5 somewhere in the memory. Let me show you. Okay, so let's create a label. We do it in .data section. Let's name it value of type dword and number 5, like this. So now if we move EAX value, we will get, let's see, we will get 5 in EAX, as expected. Now let's try to get an address of this variable, of this label. We do it with LIA instruction, load effective address, and let's check this out. Let's see what's going to happen if we run the debugger one more time. Okay, now if we step over, you can see that instead of a 5, we get this value of EAX, and this is an address in memory where this value 5 resides. Now what can we do with this address? Let's see. We can, for example, move this address to EBX, right? So let's check what's gonna happen. If we move the address to EBX, EBX is here. So first step over, you see there is this address, and step over, the same address here. As expected, nothing new, nothing interesting here, right? Now, what if we want to, because now we know how from the value we came to the address with the instruction, but what if we want to get a value that is under this address? Well, let's try it. Move ECX, and instead of saying EAX, we want to wrap EAX between square brackets. Just like this. Now if you restart, ECX is here. So look closely. EAX, EBX has the address, and ECX has the actual value. Okay, so square brackets mean that we are referring to the value under this address. Now let me show you a very simple presentation of how this works more in depth. So here is exactly the case that we just discussed. We take the value from the address that was specified in EBX and we put it in EAX. We copy it to EAX, of course we don't delete anything. But there is another option when EAX is wrapped inside square brackets. Now what happens then? See that EAX holds an address 000 etc 8, and EBX is a value. This value is not present here. If we execute this instruction, the value inside EBX will be copied to this address. So EAX has an address. We say move EAX EBX. So it is like saying move the value from EBX to the address specified by EAX. Okay, so this is basically a reverse of this. So I hope this is clear. But labels have a much greater role. They allow us to mark specified locations inside our code. They sort of work like a signposts, and they help CPU with conditions and loops. For example, let me show you how to build a very simple if statement in assembly. Let's go back to this code and modify it a little bit. Now, compare instruction is for comparing two values. EAX and value. We do it like this. So we will compare the value inside EAX with value label that we specified earlier. Let's move EAX 6, for example. And now the compare instruction works like a subtraction, but it doesn't save the product anywhere. So if we subtract EAX from value, which is 6 minus 5, we will get 1. And 1 is not a 0, so the non-zero flag will be set. Now we might ask what is a flag, because I never mentioned it before. Well, flags are these indicators that help operating system determine what's going on, sort of. They are stored in eFlag register, 32-bit register, and you have some of them and their purpose on the screen. The 0 flag that I'm talking about is the one that lets us react on the result of comparison. So we can, for example, make use of a jump instruction, and jump instruction let us move to the other part of the code that we specify. So for example, if we do jump greater or equal than jump if greater or equal, so if EAX is greater than value, all right, we want to jump to greater label. Now, greater label, we can specify down below greater, like this. And if 6 is greater than value, let's move EBX EAX. And if it's not, let's move EBX value. And here we do an unconditional jump. So no matter what the state of whatever flag is, we do make this jump to the label, let's call it end, and the label end will be here, like this, or maybe ending, because end is reserved keyword, ending like this, and we end our program here. So as you can see, this part of the code allows us to skip or execute this instruction in a specified case. So let's run it. Let me make a breakpoint here. Oh wait, I have an error somewhere. Undefined symbol ending. What do you mean? Oh, ending, not ending. Alright. Right now it's working. So registers. EAX is gonna be 6. Value is 5. Compare EAX to value. And let me show you the flags here. Compare. After the compare flag, you can see that 0 flag, it's ZR, but in the cheat sheet it's called ZF. It was changed to 0 because the result of comparison is not 0. This might be confusing, but 0 indicates false, 1 indicates true, 1 means true, 0 means false. So if 0 flag is false, this means that result of comparison is non-zero. Okay? So if this is true, if this comparison failed, if they are not equal, now we check if this is greater than the value. We jump to the greater. We move EAX, and we end the program. Alright, so what if EAX was 4? Well, probably, and not probably, but for sure, we will not execute this jump greater equal than equal instruction. Let's see. Comparison like this, and jump greater equal wasn't executed. Very interesting. We move value to EBX, so EBX is 5, and we jump to ending, and we skip this. There are a lot of those jump instructions. You have jump greater equal, you have jump lower, jump if less or equal, you have jump if above or equal, so this is like so the same. You have jump if carry, the carry flag is another flag. You have all this in the cheat sheet. As you can see, we mostly react to this 0 flag. I'm sorry. We mostly react to the 0 flag, but also there are more, mostly to the carry flag and 0 flag. But there are a lot of those jump instructions. I'm not gonna cover all of them. They all have their descriptions that are fairly easy to understand. It's just this principle that we compare two values with compare instruction, and we can react with jump instruction based on the result of this comparison. That's the key idea behind it, and that's what you need to understand. So let's make it very simple. Let's make a loop that will increment an EAX register certain amount of times. So let's first move EAX 0, and let's move ECX 5. Why ECX? Because we want to, let me make loop start label like this, and now let's compare EAX to 5 and increment. Okay, and maybe like this, jump equal ending. If not, then increment AX. And here we want to go with loop instruction loop start like this, and let me create this label ending here. Alright, so what does the loop instruction do? It takes ECX register, and each time it is executed, it makes a jump to the label and subtracts 1 from ECX. Okay, so if we now run this program, debug Windows registers, EAX 0, ECX 5, and we compare EAX to 5, it's false, so it's gonna increment EAX. Now we make another loop rotation, we go to the beginning, we decrement from ECX, as you can see, we again compare, it's not the same, we increment this, we decrement this, and it's going until we see that the ECX is 5, EAX is 5, sorry, and ECX is 0, so the loop ends when ECX is 0 or some other condition is met, of course. And we go to the end. Alright, so this is like a very simple example, but let me make something better. Let's say we have an array of 5 values, 10, 20, 30, 0, 40. And we want to check if inside this array is 0. If it is, we want to make EAX equal to 1, let's say, and if there is no 0, we want EAX to equal to 0. How do we do it? Well, first, let's move two values, one to EBX, and it's gonna be an offset of value, which is basically the address in memory of the first element of this array. And let's move ECX length of value, because as you remember, ECX is going to be decremented over time in our loop, so we need it. Now, loop start. This is our label, and under this we want to compare the word pointer EBX to 0. Now, what does this mean? We need to specify inside a comparison like this what we are comparing stuff with. Because if you just pass EBX, or more like the value under this address, because EBX is an address right now, so we want the value, you don't pass the type. It can be whatever. It can be a word, it can be a D word, it can be a byte, it can be whatever. And as you remember, compare does subtraction, and we can't really subtract different types from each other. So this D word pointer is important here, that we know that we are comparing a D word. Yeah, basically that's what it is for. So if the comparison succeeds, so if this is equal to 0, if the element that we are checking right now is equal to 0, we go to found label, and if it's not, we add EBX4. Why 4? Because this is an array of type D words, so each element is 4 bytes long. So if we have an address of the first one and we want to address the second one, we need to add 4 bytes. So we jump like this, 4 bytes, 8 bytes, and like this. 8 bytes will be here. Alright, so we add 4, and then we can access the next element in the next loop iteration. And once we do that, we loop to loop start, and if we end up, if we finish the loop, if ECX will be 0, we want to unconditionally jump to not found. Not found. Like this. Alright. Sorry. So, not found will we'll execute an instruction like this, and we're gonna make an ending label here for a return statement for just a read instruction. And here you want found label and move EAX 1, and also unconditional jump to ending, because we need to skip this. Remember, these are just labels. They are not instructions, just labels. So this is not going to be executed like a thing, but if you forget this jump, you will move from this instruction to this instruction. Like, each instruction is executed one after another. Alright, so this should work already. So let me test it. Compiled first time. This is nice. Alright, so what do we have here? We make a comparison. Of course, we should get at the 4th iteration that we found it. So not found loop, not found loop, not found loop. Now we should find it. Okay, we jump to found, we make EAX1, we jump to ending, and we return EAX. right? Because EAX is a return value. Remember it. All right, so perfect. Let's now explore the scenario when there is no 0, like this. So open up a debugger one more time. And what? As you can see, ECX was 5. Now it's 4 because we moved one rotation. But as you can see, 1, 2, 3, 4, 5. So this is the length of this array as we specified here. Okay, so it wasn't found, it wasn't found, it wasn't found. One more iteration. ECX is 0. We exit the loop. We execute the unconditional jump, not found. Move EAX 0, EAX is 0, and we return the value 0 because we didn't find 0 inside the array. And fairly simple example, more complicated than the previous one, but I hope now you understand the concept of looping conditions and arrays in assembly. But I'm always talking about this EAX, that it holds the return value, but I wasn't originally planning to do it, but let me show you how to call functions in assembly. Because let's make a very simple function, because this is pretty fun. Let's call it check, like this. It's a procedure. Remember, in assembly you have procedures, not functions to be really. It's just a naming convention. And we end procedure, check procedure with and P. Let's copy things from the main procedure to the check. And in the main, let's use call instruction to call check function. All right. And let's react to this value. Remember, EAX is a returned value, so we want to compare against EAX. If EAX is 1, we want to jump to, for example, is label, and if it's not, we want to jump to is not label, and ending here, like this. Okay. We should probably do some stuff that makes sense, but obviously not to make this video any longer. I will just maybe move some value to another register. I don't know. So if jump not equal, because this will be better. Jump not equal is not. So if it is equal, it will execute just the next instruction, and if it's not equal, it will move here. So let's now move EBX1, for example, and jump to ending. And here let's move let's move EBX 0, whatever. You should probably do something that makes sense here, but this is just to show you the call instruction. So let's make a breakpoint here, debugger, and if we check registers, you see EAX is some random value, and there is no 0 inside this array, okay? So we call check function, and EAX is 0. And now we react to EAX. It's 0, so EBX is gonna be 0. If you go here and type 0, restart, debug Windows registers, EAX is again some random value. We call check, and EAX is 1 because there is 0 inside this array. So we called a function inside our main procedure. And then we can react to the value that it returns. Of course, as you know from other programming languages, functions may have parameters, may have local variables. They are fairly complicated stuff. And this is a little teaser for the next video, because in the next assembly video, I'm going to show you how to use functions in Windows API in assembly. So Windows API functions inside assembly. This is gonna be a part 2 video to this one and to the Windows API video that I made a couple weeks before. So definitely go check it out if you don't know what a Windows API is, for example. But yeah, so stay tuned and subscribe so you don't miss it. But the most important thing that you need to remember is that people learn by practice. If you watch this video to the end and you think that you now know assembly, well, you don't. You need a lot of practice, as I do, because I learned, for example, by explaining things to the others. So I've learned a ton just by doing this video, but I also wrote a lot of this code, much more that you see in the video, so that I can explain it to you. And you should do it the same. Write code. Make your own versions of the examples that I showed you. Build upon them. If I was checking for the 0 inside the array, check if there is any negative value inside this array. Or, I don't know, check for, instead of for numbers, check for strings, because you can do it too. And so the most important thing is practice. Without practice, you can do nothing, pretty much. So it doesn't matter how many courses you watch, how many hours of videos, or how many books you read, you need practice. And with that in mind, leave a like and a comment under this video so that I know if you liked it or not. If you have any feedback, or maybe you didn't like this video, also tell me in the comments, and see you soon.